Hello, everyone. I'm going to be walking you through Unit 4, Topic 1 notes now over chemical equations. As I stated in my instructional video, there is a handout that goes along with these notes. If you do not have that handout available, or if for some reason maybe you lost it, if you were in person and now you're absent today, or if you don't have access to a printer at home and you're a cloud student, you can write all of the notes down in their entirety on regular notebook paper, but you will have to write down everything that's on each of the slides, with the exception of just a couple of things that I'll point out as we go. I am going to go ahead and walk you through the same warm-up that I'm going to be using in my in-person classes today so that everybody kind of gets a preview, and it also includes some important information that you'll be using in the notes. So our learning target for today is going to be to identify the parts of a chemical equation, and we are going to be turning a word equation into a chemical equation. What I would like to make sure that you do at this point is go into either your folder or into your Google Classroom and open up your periodic table and polyatomic ion list. So I've got that Jamboard periodic table that's in Google Classroom, and there's also a polyatomic ion list located in Google Classroom. You might have these in your folder, though. If you are absent today and you normally are in person, you probably have these handouts. Otherwise, you can just pull up the digital version in the background. So the first thing that we're going to look at is, what is a diatomic molecule? And then I'm going to also ask you which 7 elements exist only as diatomic molecules. And I'm not going to give a lot of instruction in this. What I really want to do here is I'm going to pause, and in the Edpuzzle, I'm going to ask you to type your answers in. You should just be able to do a quick Google search to be able to find the answers to these. So go ahead and search for those now and write your answers down and record them in the Edpuzzle video. Okay, so what you should have found is that a diatomic molecule is just like what it looks like. So I'm going to go ahead and pull up this pen. The prefix di means 2, right? So if I have di and then I have atomic, I'm going to have 2 atoms. So these are going to be specifically molecules that only exist in isolation as 2 atoms together. They pair up. So when I say diatomic molecule, I'm going to say 2 atoms that will always bond. Oh, I'm actually going to include this. 2 identical atoms that bond to form a molecule. So you probably have something similar to that you found when you did your Google search. It probably won't be those exact words because honestly, I just said those off the top of my head. I just broke down the word itself. But you should have something that's pretty similar to that you found in Google whenever you did your Google search. So the second part, though, you should have looked for 7 elements that exist only as diatomic molecules. And I'm going to write these down in the order that I remember them, and I'll explain to you here in just a second how I remember them in that order. But you should have found that it's bromine, then iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So I wrote them down in this order because when I look at this, I say Brinkelhoff. This is how I learned it in college. Whenever I say, what are the diatomic molecules? I always say Brinkelhoff. And it sort of sounds like a little, I don't know, like chemistry leprechaun or something, where it sounds like it's sort of my own little mascot. And I love to use it for things. So Brinkelhoff is what tells you all of the elements on the periodic table that only exist in pairs if they are ever left alone. That means if bromine is ever by itself in nature, it's going to actually come as Br2. There's no such thing as just Br. It doesn't, when bromine is found, which it's a liquid at room temperature, every atom is going to actually be paired with an identical bromine atom. You'll never just find a Br atom. It would be Br2. I will never find just an iodine atom in nature. It would be I2. I would never find a nitrogen atom by itself in nature. It would be N2. Now, that doesn't mean that these can't be in bonds, because they can. And if they're in bonds, they don't have to have a 2 as their subscript. But if they are alone, if they are in isolation, they will always be in pairs. So that's what a diatomic molecule is. And these 7, Brinkelhoff, are going to be all of the elements that exist as pairs if ever left alone in nature. So this is how you'll actually see them. All right. So now what we're going to do, and I do have a little bit more to explain about these on the next slide because I wanted to point out where they are located on the periodic table because there is kind of a pattern for their location. So make sure your periodic table is open so that you can see it in the background. And I'm going to show you what to do with those. Okay. Oops, I didn't mean to start that timer, sorry. When I click on it, it just does it. Okay, so on the periodic table, you'll notice that there's a 7 over here. So all of the Brinkelhoff elements appear in this 7. So they're going to be the halogens, except for the astatine, nitrogen, and oxygen, but also hydrogen gets thrown in there as well. So I actually heard something once that said it's all the gens on the periodic table, all the halogens, the oxygen, the nitrogen, and the hydrogen. If that helps, I don't know. But I just say Brinkelhoff. Just notice that this is where they are. They're highly reactive elements, which is why they do not ever appear alone. This is how it would look. So if I were to ever see oxygen gas written down somewhere, like in a word equation, which we're going to see what those are here in just a second, I know that oxygen gas never comes as just O. It would be O2. If I ever see hydrogen gas, it would be H2. If I ever see nitrogen gas, it would be N2. Every time I see one of those elements that is just the single like name of the element, I know that it's going to be with a 2 as the subscript. Notice that oxygen doesn't have a 2 here, so it's allowed to be in a compound without having the 2 as a subscript. It just can't be alone without the 2. Here it's in another compound. It's got a 3 as the subscript, and that's okay. It's allowed to have a 3 as the subscript. What it can't have is just a single oxygen. It's got to have that 2 if it's ever alone. But there are other elements on the periodic table like magnesium and iron that were in these compounds that don't have to have subscripts. They are not diatomic. So if I ever see just the word magnesium, I know it's just Mg, or just iron, I know it's just Fe. I just can't see the word oxygen and think it's just O because that doesn't happen. All right, so now we're going to pick up with the handout that I had linked for you in the calendar in Google Classroom. So this is the point where you are going to be copying down either the whole slide onto notebook paper or filling in the information that's on the handout in front of you. Notice that I do have words that are in red because those words in red are what will complete all of the missing information from the handout. So if you are writing this down completely, you have to write everything on the slide. But if you have the handout printed, all you have to do is look at the red words and figure out where they go in the missing, here, I think it's here. This missing information is going to be filled in with the red words that are in the slides. So go ahead and pause here and write down all of the information from this slide. Okay, so we're going to be talking about chemical equations, and in order to lead up to a chemical equation, we're going to start at the most basic form of an equation. Keep in mind that an equation in chemistry is a lot like a sentence in English. It's going to tell us using like formulas and things like that what's happening in a reaction. It's sort of the sentence that describes a reaction without using like whole words for the most part. So when I look at an equation, it's basically telling me a story. And just like a sentence in English has different parts. It has a noun and it has a subject and it has a verb and a predicate and it has adjectives and adverbs and beginnings and ends and periods and capitals and all those things that are in a sentence. We have lots of things in equations that we're also going to learn what they mean and how to label them today. We're going to start with the most basic though, which is called a word equation. And a word equation describes all of the substances that are involved in a reaction, literally just using words. You probably won't see any symbols at all. You won't see any arrows. You won't see any kind of chemical symbols. It's going to be words alone. So it's the real sentence that tells the story. So an example of this would be if I were trying to tell you what the equation or the word equation for the formation of water is, I would say hydrogen gas reacts with oxygen gas to produce water. So this doesn't tell me a lot. It really just tells me a sentence, but it's not very specific. It doesn't tell me how many atoms there are. I don't know what the formulas for all the substances are. I don't know what state of matter they exist in. All I know is kind of the gist of it. Here's what's happening. So I'm just going to put it in words. It's not enough. If I were comparing this to a recipe, which is what I usually do when I teach it, and I were to tell you, go into the kitchen and bake me a cake. And you'd say, what do I need to bake the cake? What's the requirement? Because what's the recipe, right? We need a recipe. And that's really what an equation is. It's a recipe that describes how I can make a reaction happen. So if I were to send you into the kitchen and say, okay, bake me a cake, and the recipe says you're going to need some flour and some sugar and some of the things in your spice rack, and you'll probably need, I don't know, some of the oils that you might have in your house, and maybe some eggs, probably some milk. Okay, now go bake me a cake. And you go in there and there's just not enough information. You can't get it done. It's missing a lot of details that you really need. So, like, what kind of flour do I need? Self-rising flour, cake flour, all-purpose flour? What kind of sugar? Do I need powdered sugar, brown sugar, granulated sugar? What kind of spices from the spice rack? Do I need cinnamon? Do I need vanilla? What do I need? Be more specific, Miss Herod. And so I said, okay, we can do that. And we move on to, and I keep going backwards for some reason, the next type of equation. So go ahead and pause here and fill in your missing information. All right, so a skeleton equation is just like it sounds. It's the bare bones. Like, I could maybe figure out how to bake a cake if I had this information alone. It might not taste perfect. I'm missing something. So a skeleton equation tells me the gist, but it's not enough. It uses formulas instead of words. So I just took the words that I had. So if you look at my example here on the screen, I had the words hydrogen reacts with oxygen to produce water. Hydrogen reacts with oxygen and water comes out. So I know that's the gist of the reaction. And if I take those and I put them into formulas of chemicals, then I can get closer to knowing exactly what happens in this reaction. I also know that hydrogen is in Brinkelhoff. It's the in Brinkelhoff. So when I write hydrogen down, sorry. Donna Hare to the front office. Donna Hare to the front office. When I write hydrogen down into an equation in formulas, I have to record it as H2 because it's in Brinkelhoff. And it's reacting with oxygen. So when I separate hydrogen from oxygen, I'm going to go ahead and just put a plus sign in between there to show that they're reacting together. And oxygen is also in Brinkelhoff, so it's going to go as O2. And they produce water. So in a chemical equation, I'm going to use things like arrows to show the direction that the reaction is happening. This side of the reaction is going to do the reacting, and then the arrow points to show what I get at the end. And I know that water is H2O, and so I can write my skeleton equation showing only the formulas instead of the words of the reaction that is occurring. But there's a problem. The problem with this is, where did the other oxygen go? Why are there two oxygens that did the reacting, and on the right side only one oxygen comes out as water? Shouldn't it be H2O2? But H2O2 is hydrogen peroxide, and I know that hydrogen peroxide is going to kill you if you drink it, whereas water is, a requirement for life. So adding that extra oxygen onto the formula is actually going to really make a huge difference in what I just made. You can't add a 2 on the O because you completely changed your chemical that you ended with. So where did it go? Because I know that the law of conservation of mass says I can't create it or destroy it. I have to have that oxygen somewhere. I have to account for it. And that is where now, if I have my recipe that says I need all-purpose flour, I need large eggs, I need 2% milk, I need vegetable oil, I need cocoa powder, I need vanilla extract, I need granulated sugar, all the things that are very specific. But the one thing that I didn't tell you is how much of everything you need. And that's the problem with the skeleton equation. It tells you what you need, it's specific, but it doesn't tell you how much. So the one thing that I leave out of a skeleton is the relative amounts. How much H2 is required for this recipe? How much O2 is required? And how much H2O do I get out at the end? So then we move on to a chemical equation. So go ahead and pause here, fill in your missing information, or copy down the screen. So chemical equations use the formulas, but now I also have something else. I have something called a coefficient. And in math, you know that a coefficient would be something like if I were writing down 2x, for example, in front of a variable is what my coefficient is. And sometimes I have a coefficient even in front of parentheses. Maybe I have x plus 1. and the coefficient is going to be the number that goes in the front of the parentheses. So I know that coefficients are going to be the numbers that go out in the front. And in a chemical formula, a coefficient is going to be the number that goes in front of the chemical formula for each reactant and each product. And we'll explain what those are in just a second. But the difference between the skeleton equation and the chemical equation is going to be the coefficients. Because now, and just like in math, if a coefficient's in front of parentheses, it's distributive and it multiplies the things inside. If a coefficient is in front of a formula, it multiplies the subscripts, and it tells me I started with 4 hydrogens here, and I had 2 oxygens, and I ended with 4 hydrogens, and that 2 also counts for the oxygen. So everything ends up working out. If I were to draw this, oops, I thought I was erasing. I was not. To represent it with atoms, like pictures of atoms to show you how it actually works, I could have a hydrogen bonded to a hydrogen, but I would need 2 of those, 2 molecules of H2. And then I would have, let's make these blue, or purple is fine, 1 molecule of O2 where the 2 oxygens are bonded to each other. And then at the end, I ended up with 1 water molecule that looks like that and another one that looks like that. So that's why it all works out. All of my hydrogens and my oxygens are accounted for. Okay, so that's a chemical equation. All right, moving on. Now we're going to label all the parts of it. So I'm going to do this kind of quickly. You're just going to walk through it with me. So first of all, the one thing that I'm going to point out is the left side of the equation is separated from the right side of the equation by this arrow. And the one thing that I think I stress a lot when I'm in person is every time somebody says the arrow, they always want to say equals, because gosh, since elementary school, we've been saying this plus this equals this. So when you say 2H2 plus O2, they want to say equals 2H2O. And that's actually not true. They don't equal each other. This is a story. This is a recipe. It's telling me what I had at the beginning and what I ended with at the end. So they don't equal each other. The left side is going to make the stuff on the right side. So you can read it in one of 2 ways. You can either read it as yields. So I'm going to have 2H2 plus O2 yields 2H2O. Or you can read it as reacts to produce. But what you should not ever say when you are writing this down or reading it out loud is they equal each other. So 2H2 plus O2 react to produce 2H2O. So that's the way that one should be. All right, the next thing that I'm going to look at is the stuff on the left and what that is called. So the initial substances in a chemical reaction or in an equation are called the reactants, and reactants do the reacting just like it sounds like. Missed my C there. They are reactants. Anything that is to the right of the arrow is called a product. So you could have more than one product, and most of the time you will. So all of the reactants, and they will be separated by a plus sign if there's more than one, are on the left if the arrow is pointing to the right. Now you could flip that arrow around and make the right side point to the left, and then the reactants and products kind of flip roles. So you would have reactants on the right and products on the left. But right now, since my arrow is pointing to the right, the things in the beginning are the reactants, the things at the end are the products. And you could have more than one, but if you do have more than one, they will be separated by an arrow. Now this big number, we already talked about what that is. That is called a coefficient. And what the coefficient does is it tells you, that is a terrible... It tells you the number of molecules that you have or number of compounds. How many total compounds do I have of H2? I also have this little 2, which is called a subscript. And that is going to tell me the number of atoms. The next thing that I'm going to point out is this little arrow or this little triangle right here. So first of all, any time that I have something that appears over the arrow like this does, what that tells me is it's not a reactant, it's not a product, but it does play a part in the reaction in that it's sort of like a hand holder. It's going to grab hold of all the stuff on the left and quickly pull it over to the right-hand side. So if I ever put anything over the arrow, anything at all, it's going to be what we call a catalyst. Typically, a catalyst is going to be like a formula of a compound that has to be added to make the reaction occur more quickly, but it doesn't change itself. I say that it doesn't play a role in the reaction because whatever you put in that's a catalyst always comes back out at the end to be exactly the same as it was in the beginning when you put it in there. It doesn't change form. You always get it back. So if I put 5 milliliters of water in as a catalyst, I'm going to get 5 milliliters of water back out at the end as a catalyst, or that was the catalyst. It's going to come out. So whatever's there, it's just a hand holder. It makes it happen faster. This specific hand holder, this specific triangle stands for heat. If you have a triangle over the arrow, it tells you that heat has been added to make the reaction happen more quickly. Now, a catalyst doesn't have to be heat. It can be heat because heat does make things happen more quickly, typically. But it could be anything. As long as it appears over the arrow, you know it's going to make it happen faster. All right, this L and this G. These are going to be states of matter because we learned a long time ago that there are a few states of matter. There's a liquid. So that's going to be liquid water, and there's a gas. And of course, we know there's another one, and that's a solid, and that's actually going to be on my next screen. So make sure you have everything labeled here before I move on to my other slide. All right, moving on. Maybe this just takes forever to erase. Should have probably just done this on my big board so it wouldn't take so long. All right, so the next thing that we are going to do on the next screen is label anything that did not appear in this equation, but could appear in another equation. So if I ever see it, I will know what it means because you will see each of these things from time to time. I'll just erase it once I get there so that you all can move on to the next screen. All right, so go ahead, pause here, and copy down what is on the screen. All right, so let's talk about them. So we already said that an L was a liquid and a G was a gas, and those are states of matter. But we also know that there's also a solid that exists as a state of matter. But what every once in a while, actually more often than not, you're going to see this AQ appear after formulas. And what that means is it stands for the word aqueous. Aqueous means that whatever that ionic compound is that you have in that particular equation is dissolved in water. Because ionic compounds we know are in a crystal lattice and they cannot react unless they are dissolved in water and we free those ions up to move. This double-sided arrow stands for a reversible reaction. However, I will tell you that typically it doesn't look that way. It's two half arrows that point in either direction like that. So make sure you write that down. I didn't have a half double-sided arrow like this in my list of symbols that I could use. All right, and you already know that the triangle represents heat. All right, now the very last thing that you have to copy as far as words go, I believe, is going to be from this screen, and that's the definition of a catalyst. So go ahead and pause here and copy down that definition. All right, what I wanted to point out here is that a catalyst speeds up a reaction, and what it does is it makes it easier for the reaction to happen. I included this energy diagram. We actually will talk about this later in the unit, but an energy diagram just shows you if it requires this blue hill of energy for the reaction to occur, what a catalyst does is it makes that hill lower, and it makes it easier for the reaction to happen. If it doesn't require as much energy to happen, it's going to happen much more quickly and easier. I also showed you here at the bottom of the screen that a catalyst will appear over the arrow, but it's not always a triangle. Like this one on the left, for example, has H2O above the arrow because for this particular this particular reaction, water is a catalyst. So anything that acts as a catalyst in a reaction will appear over the arrow. It's not always heat. Heat does usually make things happen faster, but it could be other things as well. All right, so what I want you to do is instead of making this a group task because you're an individual at home, we're going to walk through these questions together. So we're going to look at Before I move to the next screen, because I can't really do anything until I've moved on to that next screen, actually, I might go ahead and freeze this and snip it. All right, and now I'm going to go back here and go backwards in my... Okay, so the first thing we're going to look at is looking at these reactions that I'm going to put back up here in just a second. Which ones yield products in different states of matter than their reactants? So in order to answer this question, when I look at this, I'm looking at the reactants, which are on the left, and I'm looking at the products which are on the right. And the question was, which ones yield products that are in a different state of matter than the reactants? And so you should have, since the state of matter is what we see here at the end, you're looking for some that have different symbols or different letters from left to right. So A is going to be one. And then in part B, we have a gas, we have a gas, we have a gas, we have a gas. So those are all going to be the same state of matter. In C, we have a solid, we have a solid, we have a solid, also the same state of matter. We have aqueous, 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 and oh, look at that, a solid. So the products for this one will have different states of matter than the reactants. So you should have had A and D for that particular question. Make sure you've written that down before we move on to the next question. All right. The next question is, which equations use a catalyst? And what does that mean? So if we look at these three, if it uses a catalyst, the catalyst will appear over the arrow. And as you can see, we have a catalyst here. We have a catalyst here. It's hard to see because it's kind of in the way, but those two are the ones that have something that appears over the arrow. And what that means is it's going to make it happen faster. So number 2 should have been B and C. And number 3, name an ionic compound that is involved in reaction C and name a covalent compound that is involved in reaction B. So reaction C, to know that it's ionic, it has to be a compound first of all. So we only have, this is an element. Sorry. This is an element. This is a compound. That's ZnI2. It's hard to see. So the first thing I need to look at is this ionic or covalent? And I would know that by looking to see if it has a metal in it or not. Since zinc is a metal, this should have been an ionic compound. The other part said, name a covalent compound that is in reaction B. Reaction B. So this is an element because it's just oxygen. So the other 3 are compounds. And believe it or not, none of them contain metals, which means all of them are covalent. So that one should have been all. You could have put any of those 3 or all 3. Okay, moving on. All right, guys, I'm going to walk through 3 examples of these word equations, turning word equations into chemical equations. And then I'm going to ask that you practice 5 that are on the handout that's linked in Google Classroom on your own. And you can just copy those onto your notebook paper to complete that assignment. So the first thing I need to look at is when adding sodium to water, it produces sodium hydroxide. So I need to start by identifying which ones are reactants and which ones are products. So it says it produces, I'm going to actually snip this screen too. Let's do a full screen snip. Make that bigger. Since this says it produces, I know that this is a reactant and it reacts with water. So those are both reactants, and this is going to be a product. So when I do these, I start by putting my arrow, and now I know which ones will go on the left and which ones will go on the right. When I go to the periodic table and I find sodium, I can see that it is Na and it's all alone. And then sodium here is reacting with water, and I know what water is. So let's go ahead and put those 2 things in. Sodium is Na, water is H2O. Now, if anything is an ionic compound, I also know that to make the formula, I have to find the charges and crisscross them. Good news, neither of those are ionic, so neither of them require charges to crisscross. However, when I make sodium hydroxide at the end, and I know that sodium is Na because I just wrote it, and hydroxide is a polyatomic ion, and when I go to my polyatomic ion list, I find that hydroxide is OH, and it has a -1 charge. So when I put it down, I'm going to put OH. And remember how we wrote these, parentheses with a -1 outside of it. But I also know that if it's an ionic compound, and it is because it contains a polyatomic ion and a metal, that I would find the charges of both, and sodium's a +1 charge because it's in the first column, and see if I need to crisscross. Well, good news, it's neutral. So there's no reason to crisscross anything. All I have to do is get rid of the charges, and it's done. So this is what your first one should have looked like. All right, next. Zinc and lead 2 nitrate react to produce zinc nitrate and solid lead. So I'm going to have zinc as a reactant, lead 2 nitrate as a reactant. Zinc nitrate is a product because it's produced, and solid lead is also a product. If I put my arrow in the middle, I start by putting my reactants on the left. When you go to the periodic table to find zinc, it's Zn. It's an element. It doesn't have to have any crisscross charges because it's not in a compound. Lead 2 nitrate is an ionic compound. I know that because lead is a metal. When I go to the periodic table, its symbol is Pb. What does this 2 mean? That means that's the charge of it. Nitrate is NO3, and the charge of it is a -1. So after, and I got that NO3, by the way, from my polyatomic ion list that I also have in Google Classroom. So nitrate is NO3 with a -1 charge. So since this is not neutral, I'm going to crisscross the charges. I'm going to get Pb with a 1, but I don't put 1s, and then the 2 goes down to become the subscript for the nitrate. So that's going to be just the left-hand side. Oops, I thought I was erasing. But when I get to the right, now I need to get zinc nitrate, and zinc is going to be bonding with nitrate, which I just found on my polyatomic ion list. Oops, that is not what I wanted. Is NO3, and I also know that NO3's charge is a -1. Well, it works out that on the periodic table, zinc's charge is a +2. I wrote that down on my periodic table. When you go to the periodic table that's in the Jamboard, then you can see that it's already listed right here with zinc as a +2. So I am going to crisscross the charges, and I will get Zn 1, but I don't put 1s, and then NO3 2. All right, and then next door, because I have 2 products, will be solid lead. And if you want, you could go ahead and stick an S on there and make it all solid. Last but not least is aluminum oxide and solid iron. Aluminum is Al on the periodic table, and oxygen or oxide is O. However, I know this is an ionic compound because aluminum is a metal and oxygen is a nonmetal. Aluminum's charge is a +3 and oxygen is a -2. So I'm going to have Al with a 3+. Remember, you're only doing this with ones that are ionic, and O is a -2, so it becomes Al2O3. All right, now aluminum oxide is a reactant. No, it's not a reactant. It says it's produced. Put in the wrong spot. Let's move it. Sorry. I know I just had that there. Why is it not erasing? There we go. All right, so now let's try that again. Al2O3 is going to be over here. It's produced with solid iron when, so this is a product, this is a product. When iron 2 oxide is a reactant, reacts with solid aluminum. So iron, actually it's iron 3 oxide, sorry. Fe, and that 3 means it's iron with a 3+ charge. Oxygen's a -2. We crisscross to get Fe2O3. And then solid aluminum is going to be my other reactant. So I end up with Fe2O3 plus Al yields Al2O3 plus Fe. All right, you have 5 of these that are on the handout that is linked in Google Classroom. It looks like this at the very end. There are 5 practice problems. I would like for you to try to do these. I will probably walk you through some of the answers for these at a different time in a different video. Please let me know if you have any questions. I will be teaching this live all day. So if you've looked at this and you don't know what to do and you need to meet, I can probably open the meet and we can do it live that way. I hope you guys have a great